Hello, this is Evie with the channel Dihydrogen Monoxide. I like to post videos demonstrating basic orbital mechanics using Kerbal Space Program. On one of my videos demonstrating a bi-elliptic transfer, I received a comment asking about the mathematics that I used for the determination of that maneuver. In that specific video, I didn't use any, because Kerbal Space Program has integrated trajectory planning, meaning if you plot a maneuver node, it'll show you your trajectory ahead of time, and of course give you your apogee, periapsis, an entire updated dossier of your orbital information. But of course, NASA scientists, they don't do that. Well, they kind of do, and they have computers that do that. But they all know the math, orbital mechanics. So this video is more or less in response to that comment, and here I intend to demonstrate exactly how you would plot the delta V required in order to perform a transfer like this. So, first things first, you have to establish the scenario. You're trying to perform an orbital transfer from one orbit to a different orbit, usually of a different altitude. So it'd be a circular orbit, different semi-major axis. You can do this either ascending or descending, meaning going from a further out orbit to a closer in orbit, or a closer in orbit to a further out orbit. In this particular video, I will be demonstrating an ascending bi-elliptic transfer, meaning going from a lower orbit into a higher orbit. If we consult our, our diagram here, I've more or less drawn out the steps of the transfer. Beginning with our red circle, that will be our starting orbit with a mean sea level altitude of 70,000 meters. The specific reason I've plotted these orbits by their mean sea level altitude instead of their semi-major axis altitude is because in Kerbal Space Program, your altitude readout is provided in meters above mean sea level. So this will more or less serve as part of an exercise to convert mean sea level altitude into semi-major axis. Continuing forth to our green circle, that will be our target orbit at an altitude of about 100,000 meters or 100 kilometers. There are exactly 3 burns used to initiate this maneuver, the ascending bi-elliptic transfer, and the first one is a prograde from our starting orbit to extend our apoapsis to approximately 15 times the altitude of our starting orbit. That is in terms of semi-major axis, not meters above mean sea level. In this particular case, for simplicity, I've elected to make that altitude about 2 million meters. Once we reach our apogee, because this is an ascending bi-elliptic transfer, we engage another prograde burn to extend our periapsis to the altitude of our target orbit. Once we complete half of a period and descend down to our periapsis, we then perform a retrograde burn in order to bring our apogee down to the same height as our periapsis, hence completing the bi-elliptic transfer. However, the question arises, precisely, how do we know how much delta V we need in order to perform this maneuver? And in order to do that, we need to take great advantage of an equation called the vis-viva equation. The parameters of this equation are your gravitational parameter on Kerbin it's about 3.53 times 10 to the 12, your semi-major axis, the semi-major axis of your orbit, and your radial, or your distance from the center of the planet. With these parameters, it determines exactly how fast you would be moving at that point in your orbit, provided the parameters of your semi-major axis and distance. So what we do is we compare the speed that we're traveling to the speed that we need to be going in order to have been in the next stage of our orbital transfer. So, for example, at our starting orbit of 70 kilometers, we must first transfer this from kilometers to radial or semi-major axis. In this case, I have a Python tool to help us out with that, which gives us an absolute radius or distance from Kerbin Center of about 670,000 meters. Now, because it is a circular orbit, the semi-major axis and the radius are exactly the same. So, next, we are able to send these values forward into a vis-viva equation. For those who don't know, the vis-viva equation is defined as v squared equals the gravitational parameter multiplied by the product of 2 over your radius minus 1 over your semi-major axis. And if we pass our, I have made a mistype. I'm so sorry. If we pass our parameters into this itty bitty calculator, it returns our orbital velocity in our starting orbit, which is just short of 2,296 meters per second. In the real life context, there is a usual margin of error of multiple meters per second, but because this is a Python script, of course, you get a very high precision floating point value. In real life, of course, for spatial maneuvers, we're nowhere near this precise. Now that we've determined how fast we are traveling in our starting orbit, we must determine how fast we must be traveling at the point of our prograde to initiate our transfer orbit. In other words, we must determine the semi-major axis of our transfer orbit. Conveniently, I've made a tool for that. So, your semi-major axis, it's a property of an ellipse. It is simply the average of the two extrema values from the center of the ellipse, right? Or I guess technically a focal point of the ellipse. And in this particular case, because we have a tool, it's rather easy to determine. There's no, math that needs to be done. The radial of our periapsis, very simple, 670,000 meters. The radial of our apoapsis will be the radius of Kerbin appended to our apogee altitude above mean sea level. So in this case, that would be 2,600,000 meters. Which gives us a semi-major axis of, apologies, I have poor eyesight, 1,635,000 meters. Now that we have our semi-major axis and we have our radial, which is simply the radius of our starting orbit, we can then pass this directly back into a vis-viva equation to determine exactly how fast we would be traveling if our periapsis was at the altitude of our starting orbit and our apogee was at the altitude of our first transfer. I'm going to perform this calculation now. Based off of the calculations demonstrated in front of you, we've determined that in order to have an orbit congruent with our transfer orbit. At our periapsis, we must be traveling at about 2,895 meters per second. In order to determine the amount of delta V required to go from our starting orbit to our first transfer orbit, we simply take the difference between the vis-viva velocity of our transfer orbit and the vis-viva velocity of our starting orbit. Meaning to say, we perform 2,895 minus 2,295, which evaluates to approximately 600, meaning you would require 600 meters per second of delta V in order to extend your apoapsis up to a 2 million meter radius above mean sea level. The next step of the operation is to simply determine how fast we must be traveling all the way up here in order to have our periapsis extended to the altitude of our target orbit. In such case, you simply perform a very similar equation, but instead adjusting the periapsis of your semi-major axis from your starting orbit to your target orbit, meaning to say, we will simply perform a semi-major axis calculation. The radial of our periapsis should be about 700,000 meters because our distance from mean sea level is 100,000 meters and Kerbin has a radius of 600,000 meters. The radial of our apoapsis, it'll be the same as it was before, 2.6 million meters, which gives us a semi-major axis of 1,650,000 meters. As you can see, that is not significantly different from the semi-major axis of our first transfer orbit. That's entirely normal because we are only ascending 30,000 meters as per the maneuver. The next step of the operation is to perform a vis-viva equation such that we know exactly how fast we would be traveling if we had the aspects of our second transfer orbit. So the first step is to, of course, pass the semi-major axis of our second transfer orbit, and then to pass the radial distance from our center mass, which in this case is, as it's been for a while now, 2.6 million meters. And that gives us a velocity of 759.1 meters per second. Retrospectively, I've neglected to calculate the velocity that we would have approaching our apogee. I greatly apologize for that. We are going to do that now. It's very simple. We just pass the semi-major axis of our first transfer orbit at the radial of its apogee. So we will perform another vis-viva equation and pass the semi-major axis of 1,635,000 meters at a radial of 2.6 million meters to see the velocity we would have approaching our apogee is about 746 meters per second. Therefore, in order to determine the amount of delta V needed to make the orbital adjustment, again, we just take the difference between the velocity of the target transfer orbit and the velocity of our approach. In other words, 759 minus 746. It evaluates to somewhere between 13 to 15 meters per second. The next and final step of the transfer is, of course, descending to our target orbit and initiating a retrograde burn in order to circularize. So what we will do is we will perform a vis-viva equation to determine exactly how fast we should be traveling in order to be in a circular orbit at our target altitude. So we'll do precisely that. At 100,000 meters above mean sea level, the semi-major axis of our orbit is of course just the radius of the planet added on to our altitude above mean sea level. In this case, that would be 100,000 meters plus 600,000 meters, giving us a semi-major axis of 700,000 meters. Our radial, of course, being that exact same value because it is a circular orbit, giving us an orbital velocity of about 2,246 meters per second. Next, we have to determine exactly how fast we will be traveling as we approach our periapsis, which is at our target altitude, from our second transfer orbit, which is very rudimentary. So we will just perform another vis-viva equation. I do believe we have the semi-major axis of that target orbit somewhere in here. Yes, we do. 1.65 million meters. Except our radial, instead of being all the way up at 2.6 million, it will be all the way down at 700,000, giving us an approach velocity of about 2,819.5 meters per second. Again, we will just take the difference between these two numbers in order to determine how much we must change our velocity by in order to circularize. In this case, that would be 2,819 minus 2,246, evaluating to approximately 575 or 573 meters per second. And that will be the completed maneuver step by step with a few misspeaks and mistakes because I'm not used to verbally annotating. In order to determine the sum of the delta V utilized throughout the transfer, you simply take the sum of the values you've accumulated through calculation to determine that this complete transfer uses about 1,186 meters per second of delta V because that is my greatest apologies. We just had a microphone error because that is the sum of 600 meters per second, 13 meters per second, and 573 meters per second. Overall, the math itself, it's very, I'm sure you've heard this term in calculus before, plug and chug like. It's very repetitive, just using the same formulas over and over for different steps of a prograde or retrograde burn. Thank you for your time.